Hello, friends, and welcome to a lecture on operation research. And today we will be again studying something different in game theory. This is Professor Arvind Prasad. What would we be studying today? Well, it's games without saddle point. Now, games without saddle point usually use a mixed strategy. So, we'll first see what is a game without saddle point, and then afterwards we'll also see what is a mixed strategy which we use to find solution to such games. So let's take up a problem. The chances of winning an election. Well, I have used this problem in other lessons of game theory. You can always go and watch them. But for the sake of completion, I'll repeat what the problem is. So we have two politicians. They are contesting from Mumbai and Pune. Now, Mumbai and Pune are two major cities in Maharashtra, India. So the strategy one is to campaign for one day in each city. That is, the either of the two politicians they campaign for one day in each city. Well, the strategy two is that they campaign for 2 days in Pune, and the strategy three is that they campaign for 2 days in Mumbai. Now, it goes without saying that they have just 2 days at their disposal. So there are obviously people who do research on what the political mood is and how the elections would swing. So they have some idea of what is the likely votes that a politician would get in case he campaigns in certain city. So this is the payoff table or for politician 1, where if politician 1 he uses strategy 1, that is to campaign in Mumbai, okay, that is in each city he campaigns one day, then what would he get? So the strategy 1 is in row 1. So if he campaigns with strategy 1 and the politician 2 also campaigns with strategy 1, okay, so the payoff to politician 1 is 0, that is neither win, okay. Now if politician 1 uses strategy 1, that is he campaigns in each city for a day, but politician 2 campaigns for 2 days in Pune. Well, in this case, politician 1 stands to lose 20,000 votes. If politician 1 sticks to strategy number 1, but politician 1 uses strategy 3, which is nothing but campaign for 2 days in Mumbai, politician 1 stands to win 30,000 votes. The next row, that is the row of strategy 2, can be understood similarly. That is, if the politician 1 uses strategy 2 and politician 2 uses strategy 1, politician 1 stands to gain 50,000 votes. Now, what is it? Strategy 2 is campaign for 2 days in Pune. So, politician 1 campaigns for 2 days in Pune and politician 1 campaigns for one day in each city. In this case, politician 1 stands to win 50,000 votes. All other entries can be understood similarly. So let's get ahead. Now, what we assume that both players are rational, that is, they could take some rational decisions, they wouldn't take irrational decisions, and both of them are aware of what their opponent's options are. Obviously, when you have 2 days and you have two cities, what are the options politicians have? Fair options, of course, we're talking about. That is, they either campaign in one city, any of the cities, that is Pune or Mumbai, for 2 days, or they campaign for one day in each city. So, mostly, both the politicians are aware of what is actually the strategies available to the other politicians. This is what we assume, and which to a large extent is true. Now, again, we go off to the payoff, go to the payoff table of politician number 1. Now, what do we find here? Now, if politician number 1 has to arrive at a strategy, he would critically look at his table. So, what would he do? He would first eliminate strategy number 3. Now, why is that? Let's go back. Now, strategy number 3, as you can see here, in strategy number 3, he stands to lose 40,000 votes if politician 2 also uses strategy 3. Now, if you take the worst case scenario for politician number 1, it is that he stands to lose 40,000 votes in case politician number 3 or politician number 2 uses strategy number 3. So, this is a strategy he would avoid. Now, he has other two strategies. So, what would he do? Now, he would try to maximize from this board. So, the maximization would happen if he could use strategy number 1. Now, why not strategy number 2? Now, in strategy number 2, remember one thing: if politician 2 uses strategy number 3, politician number 1 stands to lose 30,000 votes. But at least in strategy 1, he stands to lose 20,000 votes in case politician 2 uses strategy number 2. So, he loses lesser votes than strategy number 2. In strategy number 1, politician 1 loses lesser votes than in strategy number 2. So, he would rather go for strategy number 1. Now, this game board is available to politician number 2 also. He has done his own research. So, what would he do? Well, in this case, he would go in for strategy number 2. Why? That is because he would like to impose a loss on politician number 1. Now, politician number 1, realizing this, would again go back to strategy number 2. Because why? At least if he believes that politician number 2 is going to use strategy number 2, in this case, he stands to get 40,000 votes. But then, politician number 2, also being an astute politician, would again like to play, and he would rather take a chance of playing by strategy number 3. In this case, politician 1 loses 30,000 votes. Now, if this game board is available, not the strategies, that is the strategy and the game board, but not the final call on strategies, is available to both politicians. As we can see here, they cannot clearly arrive at one particular strategy, right? They would have to take a chance to play any strategy, and the chance might go in their favor, might not go in their favor. Now, let's analyze it a bit deeply once again. Okay, again we take the payoff table for politician 1. Now, here in row number 1, the minimum that the politician 1 would get is minus 20,000 votes. In row number 2, it would be minus 30,000 votes, and in row number 3, it would be minus 40,000 votes. Row number 2, once again, I repeat, it's minus 30,000 votes. Now, for politician number 2, in column number 1, he stands to lose 50,000 votes to politician number 1. He stands to lose 40,000 votes to politician number 2 if he plays by strategy 2. And if he plays by strategy 3, he stands to lose 20,000 votes. Now, what would be here? Well, politician number 1 would gravitate towards going towards strategy 1. But for politician number 3, he would naturally gravitate towards going towards strategy number 3. So, as we can see here, both do not meet a common strategy. That is, if politician number 1 would have used strategy number 1, okay, and politician number 1 would have also used politician number 3 for certainty, then it would have been a win-win situation for both. But as we can see here, it is not a win-win situation. The reason is, if politician number 1 uses strategy 1, he is going to lose 20,000 votes. So clearly from the minimax principles also, we can see here that the politicians really do not have much choices. They cannot arrive at one particular cell where it would be the minimum payoff to strategy, minimum payoff to politician number 1 from politician number 2's perspective, And then politician number 2 also would have to, take the minimum payoff and accordingly go away. Well, this is just not possible. So what we have now here is that, how do we analyze this problem? As we can see in the previous board too, that a mix of strategies would be used, where what you would do is you would take final call on the strategy depending on what the other situations are. So how do we assign probabilities to strategies is the main question here. If we arrive, if we make some probability analysis of strategies and then arrive at a result, maybe we'll have a clearer picture that what strategy should be given what probability, and at the last moment, how do you take a decision based on that probability. So yes, the maximin and the minimax are shown here. So as we can come here, we have no final strategy, and the game really does not have a saddle point. Now, games that do have saddle point, there's a lecture on that. You can watch that, then you'll come and understand what a saddle point is. A saddle point is one cell in such a game board where both the politicians gravitate towards the same cell, okay, the same strategy itself. But here, as we can see, that they cannot gravitate towards arriving at the best result in one particular cell. So what does the player do now? Now the player has only option to assign probability to strategies. And if you assign probability to each strategy, then the sum of the probabilities obviously should be 1. Now, remember here, probability is a likelihood. It's not a certainty. When you are assigning probabilities to a strategy, it's a likelihood that you might take a certain strategy based on its probability. But it's not a certainty. One needs to understand that values of probability do not carry certainty of doing a certain thing or certainty of some results coming over. It only shows a probability, of course. And at the final moment, you take a call based on the probability, of course. And there are other factors also. So, let's say politician 1 gives a probability value of x1, x2, and x3 to strategy number 1, 2, and 3. And politician 2 gives a probability value of y1, y2, and y3 to strategies number 1, 2, and 3. Now, the entries in the table is known as the payoff. Now, this is the payoff for politician 1, of course. And the y1, y2, y3, x1, x2, x3, they are known as the probability. So, what is the expected payoff for player number 1? The expected payoff is summation I to m j to n pij, which is nothing but the payoff to politician 1, and xi yj, where xi is the probabilities of the strategies of politician number 1 and yg is the probability of strategies of politician number 2. When finally both the politicians arrive at some probability, well, you then get an expected payoff. You will get an expected payoff of player number 1. So based on the probabilities, you have a payoff. Now, yes, let's get back now. Now, player 2, let's say what is the player 2? Now, this problem can be best solved by what could be the probabilities assigned to each and every strategy. Probability, that is the probabilities of assigning, or the calculation for assigning probabilities to strategies, is best solved from the perspective of probability or a player number 2, because player number 2 always in a payoff table for player number 1 or politician number 1, a player number 2 only keeps losing, as we can see here, and yes, in certain case he keeps gaining. So the player number 2 will assign probabilities y1, y2, and y3 to strategies number 1, 2, and 3. Always start from the perspective of player number 2 whenever you want to solve a mixed strategy problem, right? So there we have once again y1, y2, y3 are the probabilities, and you have the payoff table for politician number 1. Now let's look at it from the perspective of player number 2. He is going to choose probabilities, that is y1, y2 and y3, in such a way as to minimize summation j, that is 1 to n pij into yj. He has to minimize this value, right? He has to minimize the payoff to politician number 1. So, well, in this case, as you can see on the right hand side, the equations are written where y1 and y2 and y3 are the probabilities and nu is the payoff. Okay, now in this mixed strategy where probabilities have been assigned to each and every strategy, let us say nu is the payoff and it is the optimal payoff, right? So any calculations involving the RHS of the equation should be less than equal to nu. It cannot be greater than equal to. You cannot come to a value of probability which would be greater than the optimal minimum payoff, that is nu, in this table, which can be given to politician number 1. Well, obviously y1 plus y2 plus y3 is equal to 1 now. So we have to minimize this, that is we have to minimize the value of y4 where y4 has been replaced for nu. So how do we solve this? Well, one of the ways of looking at it is the z, that is the objective function, can be written as 1 over y4 where 1 over y4 has to be maximized because y4 has to be minimized, right? So you get this set of equations once again, and then what do you do is you have to maximize 1 over y4. So how do you go about doing it? You divide it by y4. This is the trick in solving the problem. So therefore the resulting set of equations become this, where y1 is nothing but small y1 divided by y4, where y4 is nothing but nu. So these are the set of equations we get. Now this looks in like in a proper form where one can apply simplex theory now, or linear programming rather now, of simplex theory, and we can solve this problem. So we go about it. So y4, y5 and y6 are the surplus variables that we have added now, and there we are with the simplex table where z has coefficients -1, -1, -1 for y1, y2, y3, and all other coefficients are written now. Now, if we look at the table first, we find that if we move in the direction of y2, okay, we can equally move in the direction of y1, y2 or y3, right? So we choose y2 now. If we move in the direction of y2, so the incoming variable is going to be y2 and the outgoing variable is going to be y5 because y5 has now the least ratio, right? So we do our row and column manipulations to make the column of y2 as 0, 0, 1, 0, right? 4 has to be made 1 by row and column manipulations, and the all other values in column y2 have to be 0. y2 is the pivot column and y5, or equation number 2 or row number 3 rather, is going to be the pivot row. So we do the calculations, and there we have it once again. Once again, what do is we find that we have to move in the direction of y3 because y3 has a negative coefficient in z. Now again, what do we find? The incoming variable is, or incoming non-basic variable is y3 and the outgoing basic variable is going to be y4. So y4 is going to be the outgoing variable because the ratio here is 3. And finally, we get this game board where we find that no longer there are any negative coefficients in the objective function. And then what do we get? We get the value of y2, y3 and y2. Note here, we haven't got y1. y1 plus y2 plus y3 is equal to 1. Now, what does such kind of a table mean? Let's get ahead and have a look. First, let's do the calculations. we have the value of 1 over nu, which is nothing but phi 1.5. So we have z, which is equal to phi 1.5. So therefore, this is nothing but 1 over nu. So nu is going to be, that is the optimal payoff, is going to be 1 over 6th. Now we take this value of 1 over 6th and we recalculate back y2 and y3. That is the y2 and y3 that you see here. That is the probabilities of strategy 2 and strategy number 3. So we calculate it back now. And what do we find? We find that y2 is 4 by 9 and y3 is 5 by 9. If we add it up, it comes to 1. Now, this automatically means that y1 is 0. That is the probability of using strategy number 1 is 0. Now, why do we get such results, and such results have a logic behind it? Yes, it's quite logical to get this result because as we observe the strategies of politician number 2, in strategy number 1, he will either give away nothing to politician number 1, or he might end up giving 50,000 votes to politician number 1. But in strategy number 2, at least he ends up getting 20,000 votes from politician number 1. And in strategy number 3, if you go to see, he ends up getting 40,000, as high as 40,000 votes from strategy number 1. Now, have a look at the probabilities that we have got. The probability of strategy number 1, strategy number 3 is high, it's 5 by 9. So the results are quite logical and they do have a meaning, they do add a meaning to how we should assign probabilities to the strategies. Now, having calculated these probability of the strategies of politician number 2, can we do it for politician number 1? Yes, it's simple. We know that the payoff should be 1 by 6. Now, this is the payoff that the politician number 2 would use strategies with probabilities. So, this would be the minimum or optimal payoff that you would give to politician number 1. So, politician number 1 will also have to arrive at this minimum payoff that politician number 2 is ready to accede to him. So, it's solved this way. Well, in this case, have a look. We assign x1, x2 and x3 as probabilities to strategy 1, 2 and 3, and we write these equations where nu is going to be nothing but 1 by 6th and x1, x2, x3 is going to be equal to 1. And this can be solved and we get the values 7 by 11, 4 by 11. Now again, for strategy number 1, the probability is higher. The strategy number 2, the probability is lesser, and we get also the result that the probability of strategy number 3 is 0. Do they make sense? Let's go back. As we can see here, in strategy number 1, he stands to lose only 20,000 votes. In strategy number 2, he stands to lose further higher, that is 30,000 votes. But in strategy number 3, he stands to lose 40,000 votes. So obviously, the politician 1, as we had seen earlier in this lecture, the politician number 1 would try to play by strategy number 1 and 2. And he would be more gravitating towards strategy number 1. The reason is because the loss of votes is least here. Okay. Well, if you sum it up, it's minus 2 to so there's 50-50 chance. He might either lose or he might either win, right? So there we are. So the politician number 1 will have a higher probability for strategy number 1 and a lower probability for strategy number 2. So that was the end of my lecture. I know it was a pretty long lecture, but then at the end of it, this has given you a very good idea about how do we assign probabilities in case we want to play by mixed strategies. Now remember, after you have assigned probabilities, you have assigned in a way the likelihood of what strategies you might play. Remember one thing, in any strategy that politician number 1 or 2 they play, losses are imminent. But then from the 2 strategies that you would take or 3 strategies that you would take, the one with a higher probability would minimize your loss. Okay, it would minimize. It would be there would be a greater chance that you might not lose much. Your chances of winning would be higher. Chances. Okay, it's only chances after all. You might end up losing also. So this is what assigning probability actually means. And then afterwards, assigning probability, you know, okay, the expected payoff is going to be a value. So from this expected payoff, you can understand that, okay, if you play by some mixed strategy, what could be the expected votes you might get, or what could be the expected loss you might incur, or what is the worst possible scenario you might end up with. Goodbye, friends, and have a great time. And if you find this lecture interesting, do share it to your friends. Yes, I have not shown the calculations for the system of equations that I have written for politician number 1. Why don't you solve it and do post the result in the comments? One good way of solving these problems and really getting a very good insight of them would be to use Excel or LibreOffice Calc and use the linear programming solvers available in them. But then that's a subject for some another day. I might post some videos on it. But of course, such softwares, that is either Excel or linear programming calc, you cannot use them in exams. But yes, modern calculators do allow you to do calculations quickly, and therefore you can use them. So signing off, guys. Goodbye. Have a great day.